Hey everyone, I'm Shiva. Today I'm going to present this paper titled A Review of Intelligent Design for Test Based on Machine Learning. It was published in the year 2023 by Ziyu Zhao and Zikong Cai. The paper's main objective is to explore how the machine learning techniques can be integrated into design for test. Let us start with the motivation and background behind the paper. So, in recent years, we have seen a large increase in design complexity and a rise in manufacturing costs. So, this directly impacts testing. We all know that modern chips contains billions and billions of transistors, and thoroughly testing them can be a lot time consuming and also expensive. So, as a result, we needed solutions that can deliver high test coverage, but in a shorter time frame and with also reduced costs. While design for test has its traditional methods like scan chains, automatic test pattern generation, and built-in self-test, these approaches might not work always with the continuous growth in the circuit size and also the complexity of the circuits. It has become a great challenge to work with these traditional methods. So the addition of the machine learning techniques helps in here by learning from these massive data sets, and they converge on optimal or maybe near optimal solutions more quickly than these classical approaches. So this saves both time and also resources in test generation and analysis. So the paper is structured around four core areas where ML can enhance DFT. So the first one is the scan compression, and the second one is the ATPG, and the third one is built-in self-test, and the last one is the power analysis. We're going to look into each of them up next. So across these four, the paper highlights various machine learning techniques like supervised and unsupervised algorithms, and principal component analysis for dimensionality reduction, and neural networks for pattern generation and for optimization. Let's start with ML in scan compression. So in this, the first step is data compression and parameter tuning. So here we first try out few different scan compression settings like how many scan inputs or outputs to use, and note down the resulting test coverage and the test time. So this gives us examples of what happens when we change those settings. We save the data as our training set. Next, we feed that training set into a machine learning model like a regression or boosting model, which learns the different compression settings that affect the coverage and the test time. Then instead of testing possible settings again and again, we can just ask the model like what's the best settings for this new chip design. So the model's prediction helps us to pick the ideal compression settings very quickly rather than the traditional approaches where we just do it by trial and error method. So neural networks can help doing this job by looking for patterns in the data and simply generalizing them. So by skipping a lot of guesswork, we quickly find the best balance of fault coverage and the test time. What we call this as a sweet spot. So in the end, it reduces both the testing time and also the overall cost. Coming to ML in automatic test pattern generation. So it already has few algorithms like D algorithm, path-oriented decision making, and fan-out oriented algorithms. So these all try each and every path to find the faults and generate the test patterns. So, however, for large circuits, this method might not be efficient because it involves a lot of backtracking and can be time consuming too. So, instead of manually searching everywhere, when we use a neural network, it can help us guess which paths have the highest chance of detecting the faults. And it also helps in reducing the backtracking as well. So, meanwhile, using unsupervised methods like PCA help us reduce the circuit data, like making us to consider only fewer variables, which makes it faster to generate the good test patterns. By applying these ML models, the paper notes a huge decrease in the backtracking steps, which in turn cuts down the CPU runtime. This might be especially beneficial for large circuits where even small speed ups can give us big savings in the time as well as the computing power. Coming to machine learning in built-in self-test pattern generation. So in this scenario, the chip itself generates test patterns using a linear feedback shift register and compares the output to an expected output. We all know that the LFSR is random and you get a lot of patterns that you don't really need or that don't really help you to find a new faults. So instead of letting the LFSR to just spit out some random patterns, using an artificial neural network figures out which patterns are like best at catching faults. So we can look at the circuit here. This is an artificial neural network circuit that serves as the built-in self-test design structure. It has a counter that each count value represents a potential address for the test pattern. So these addresses are fed into the both neural network circuit as well as the count circuit register. So instead of storing all the test patterns in the read-only memory or like generating them randomly with an LFSR, the artificial neural network learns a mapping from each counter value to the corresponding test pattern. I mean, this means like if you say you have n-bit address, the ANN can generate 2 to the power n different patterns by interpreting the address input. So the advantage is that the ANN's parameters consume less space than storing a large number of fixed patterns in memory. Also, the ANN can be trained to produce more effective patterns than a purely random LFSR. So in summary, using an ANN means fewer wasted test patterns and faster detection of faults. I mean, although you still need to compare with the expected outputs, but now you do it with the patterns that are most likely to catch the real problems, and I mean, it saves both time as well as the resources. And the last one is machine learning for the power analysis. So the test patterns can cause high switching activity, which leads to high power consumption. So if the chip gets too hot or is overloaded, it can mess up the test results and stresses the chip. So we need to keep an eye on the power during the testing process. This paper mainly discusses about two ML approaches for the power. The first one is regression models like linear or neural networks that helps us to predict how much power does a particular pattern might take during the test. And the next one is k-means clustering, so which helps to group these test patterns by the means of the power they use, and it helps us to spot the patterns or the groups which might be power risky that uses a lot of power. So I mean, there's also a few challenges with this, like to train these power prediction models we need a lot of detailed data on how much power each pattern might use. I mean, this can be tough to collect all this data, and if the model is tuned carefully, it can predict the power use within about 5% error. That's good, but like for large chips, we might still need improvements. So to summarize, as chips kept getting bigger and more complicated, the usual design for test methods couldn't handle all the challenges on their own. So the machine learning helps by using the data to generate tests more quickly and optimally for all the cases we have discussed earlier. And also looking ahead, we might see deeper or more advanced AI models like graph-based neural networks for really large circuits. So we'll also need better ways to factor in the timing and also area limits when checking the power usage. And we must be mindful of all the training costs of ML methods, making sure we get the real-time savings and benefits when testing the new chip designs. So that brings us to the end of this presentation. Thank you. I'll be looking forward for any questions or discussions on the presentation as well as the paper. Thank you once again.